Today I'm going to talk about some of my group's work over the past 3 or 4 years now in how we manage data movement in heterogeneous systems. I think we all know this. Don gave a good overview at the beginning of how our memory requirements are really growing, and in many cases, when I talk about memory requirements growing, I'm really talking about the size of our working sets, active working sets in our applications are getting really big. So we need this, byte addressable, low latency and high bandwidth, massive capacities that are byte addressable, low latency and high bandwidth. So the kinds of systems that we've been looking at are systems with lots of different kinds of memory. So we might have systems with traditional DRAM, with high bandwidth memory connected to the package, on the package, with things like 3D crosspoint or persistent memory connected to the package, as well as things like CXL. And so the question that we've really been asking lately is, given some data that you have that you want to work on, where should you put it? Which memory technology should you put it in? And how should you move it from one memory technology to another memory technology? What's the right time to move it? And what's the right mechanisms to move it? So in this talk, I'm going to kind of touch on a couple of different things. First, I'm going to talk about why conventional techniques that we've used as computer architects for the past 4, 5, 6 decades, why they don't work in these emerging systems. And then I'm going to talk about a couple of different approaches that our group has been working on to kind of bridge this semantic gap between the application and the hardware in order to get better performance as we're moving this data around. Okay, so to dive in, I'm going to start with why caching doesn't work. I'm going to try my best to stay within the time period here. Okay. So this is based on a couple of papers that was published at ISPAS a couple of years ago. One of them was nominated for Best Paper. Okay, so when I talk about conventional data movement, in our conventional heterogeneous memory systems, we had DRAM, which was low or high latency and kind of far away, and then we had SRAM that was on the chip and lower latency and higher bandwidth. And the way we managed this heterogeneous memory was through hardware-driven block-based caching. So these caches were great for a very long time. So they were programmer transparent. Programmers never had to worry about where their data was. They didn't have to manually move the data around. They were very low overhead. If you wanted to throw in another level of cache, it usually gave you better performance. But if we look at these heterogeneous systems and you say, want to use HBM as a cache for your 3D crosspoint, or as a cache for your DRAM, or your local DRAM as a cache for your remote DRAM, we see that there are some issues if we add another level of cache, which is based on DRAM. So let me talk a little bit about what we see. So there's a difference between SRAM and DRAM, at least when we're using them as caches. So in SRAM caches, things like the tag, the LRU, all this metadata that you need to store in order to get caches to work, that's stored in a separate structure from the data. There's a separate SRAM array. And that SRAM array, in fact, can be higher bandwidth and lower latency than your data array. And so accessing the tags doesn't really cost you anything in these SRAM systems. So you can access the tag and data in parallel. You can do extra tag accesses if you have coherence requests, et cetera. And it doesn't hurt you. But when we look at the way that DRAM caches are architected, on the other hand, this isn't the case. So there's a bunch of differences. One is that they're off chip. And so that means you have many fewer pins to get to this DRAM. Even HBM, you have fewer pins than what you would have in an SRAM cache. The tag and the LRU and all this metadata actually share the same data movement system, the same bus as the data. So if you want to check a tag, you have to give up some bandwidth to your data in order to check that tag. On top of this, just generally the bandwidth is lower to these memories, and the latency is much higher to go access DRAM than to access SRAM, or particular SRAM array. at least. So because of this, it turns out that DRAM caches just in general work really poorly. So here's some real data that we got on Intel's Cascade Lake system. Now, you could probably argue that Cascade Lake, they made some poor engineering choices in how they designed this DRAM cache. But I think that actually some of this is just fundamental to the way DRAM caches are going to work. So what we're looking at here is these purple bars are the effective bandwidth that we see at the core. So this is a read-only benchmark. We're reading something that doesn't fit in the cache, so it's much bigger. We're reading data that is much bigger in the cache. So we're seeing a lot of misses. And the effective bandwidth that we see at the core is about 25 gigabytes per second, a little bit more than 20 gigabytes per second. Now, these other bars are the hardware performance counters telling us the total bandwidth of DRAM reads, total bandwidth of DRAM writes, total bandwidth of the backing memory, which is NVRAM in this case, reads, and backing memory writes. So since we're doing read-only, we don't have any backing memory writes. But what you can see is that we're actually wasting 3 accesses to this DRAM to get 1 demand request. And so we're wasting 3x bandwidth in order to get our access. And this is just on reads. For writes, it gets much worse. So again, purple is our demand, which is about 6 gigabytes per second now. And then these other bars are the bandwidths for, again, DRAM read, DRAM write, NVRAM read, and then VRAM write. And in this case, it takes 5 accesses per demand request. So if you're doing a write-heavy workload, you're wasting 5x your bandwidth just on managing the cache, not actually getting your data out of it. And this has real-world performance implications too, especially if you look at things like training machine learning, where you're essentially doing these write-heavy workloads of having to write all your activations every single step through the training. So the ISPAS paper has a lot more details on this. I'm not going to go into that. If you're interested, I'm happy to bring up that full talk, and we can talk about it offline. But to give a quick high-level overview of our takeaways there, while hardware managed caches have been great for us in the past, looking forward with DRAM caches, the bandwidth utilization is really low whenever you have misses to the DRAM. If you have 100% hits, it works great. But when you start having misses, the performance is absolutely abysmal. One of the key reasons for this performance being bad is if you have dirty data in the cache, this is when you have to be doing all these extra metadata updates and all these extra reads and writes in order to deal with things. And so there's a lot of room for optimization. Okay, so now I'm going to jump and talk about some of the solutions that our group has been working on. So the first one I'm going to talk about was published at ASPLOS in 2020 called AutoTM, for automatic tensor movement. Okay, so my opinion is that software can kind of save us here. So hardware managed caches aren't very good because the hardware doesn't have much insight into what's actually going on. But the key idea here is that programmers know a lot about their workloads. Programmers can actually predict the future and tell you what the data use is going to be next, whereas hardware managed caches can only look at the past to try to predict the future. And really, when I say programmer, though, you should read this as the compiler, the runtime, or the experts who designed, the low-level functions in TensorFlow, these kinds of things, not necessarily all programmers. So we saw that hardware managed caches aren't very good. And they're not very good because they're kind of really fine-grained and they can't look at the future. But programs, on the other hand, they operate on objects. And we can exploit, and we will exploit in this work, statically predictable accesses to these objects in order to more efficiently do the data movement. And we can get away with this because, especially what we're going to be talking about here is training machine learning workloads. We're using these programming models that give us really good insight into what's going to happen in the future. So things like TensorFlow, PyTorch, Intel's One API. So the way AutoTM works, and I'm just going to give one quick slide on this, is that the idea is when you're training your kernels or you're training your graphs, So we have this compute graph, which has a bunch of kernels, and these kernels either produce tensors or consume tensors. And then they do their computation. And in AutoTM, we were looking at CNN training, and these convolutional neural nets, they're mostly static graphs. And so at compile time, when you're creating the graph, the computational graph, you can look at it statically and do some analysis. And so what we did is we looked at this and we said, can we find a way to optimally move and place these tensors for this compute graph? So what we did was profile each of these kernels with tensors in either slow memory or fast memory, and then set up an integer linear program and just ask the optimizer, find the optimal place for these tensors, given the constraint that there's a fixed amount of fast memory, fixed amount of DRAM. So we performed this experiment on a set of really large training workloads. So down here, we're training on the order of like 3/4 of a terabyte. This was all done in Julia. The student working on this, Mark Hildebrand, absolutely loves Julia. It turned out to be a really good system for doing this kind of stuff. And we were running on the Intel Cascade Lake, which had 3D crosspoint and DRAM. So all these workloads that we're looking at don't fit in the DRAM. Okay, so let me show you real quick how AutoTM does compared to a DRAM cache. So this is speed up compared to using the DRAM cache for training. So that means 1 is the performance of a DRAM cache. And then static AutoTM and synchronous AutoTM, these are using the software to do movement between DRAM and 3D crosspoint. And so what we can see is that for these more complex CNNs like DenseNet, we get up to 3x performance over a hardware cache of managing this data movement ourselves. And this is even in the case of synchronous AutoTM was actually doing stop the world, move your data, and then start the world again. There's no overlap between data movement and computation in this case, and we were still able to get 3x performance. If we had some hardware help, we might be able to do overlapping data movement and computation, but we didn't look at that in this work. Okay, so why does AutoTM win? So the DRAM cache is direct mapped in this system. And so we ended up with a lot of conflict misses, essentially, when it doesn't, when you have an array that doesn't fit in a direct mapped cache, and then you start reading just beyond the size of the cache, it starts to really hurt you. In the DRAM cache, bandwidth is really poorly utilized on misses, as I was talking about before. Not only do you have a lot of extra accesses to the DRAM, but also the traffic to the backing memory is really poorly shaped. You end up with essentially random accesses to that backing memory because you're randomly evicting things, or not. It's not random, but it's not well behaved what's being evicted, and so the bandwidth to the backing memory suffers as well. And another really interesting thing that we saw with this is that by adding some of this semantic knowledge into the data movement, we were able to take advantage of other kinds of optimizations. So, for instance, we found that we could actually skip writing back a lot of the data. So you during your forward pass, you wrote all the activations. On the backwards pass, you used those activations. Well, there's no reason to write back that data to the backing memory if you've already used it. So you can just elide those write backs, and that saved a lot of performances. Again, that was published at AskClass. That paper has a lot more details. Okay, so I want to briefly talk about generalizing this idea. And this was in Mark's dissertation, and actually a piece of this we just found out will be published at ISC coming up this year. Okay, so the idea here is that in order to generalize, what we want to do is try to separate the concerns between the mechanisms of data movement and the policy that we're going to use to move the data. So the idea is at the high level, the application of the runtime, it understands things like objects. It understands that we're going to read something, going to write something. We're never going to use it again, or there's going to be a long reuse between these objects. And so what we want is for the application of the runtime to be able to use these kinds of high-level data management interface or data management API calls to say, this is how the data is going to be used. Then at the low level, we can implement some kind of data management interface at the low level, which actually does the movement between fast memory and slow memory. Or it tells the hardware this is dirty, so you're going to have to write it back at some point. Or it links things together between fast and slow memory to say, here's a copy, which is in both. So we took this idea and we implemented on top of one data manager, which again was in Julia on Intel's Cascade Lake with 3D Crosspoint and DRAM, but we implemented two different policies for two different kinds of workloads. Oh, so here's a quick little example. So here's the data management API in Julia, which is complex and has lots of the low-level API, which is complex and would be hard for a programmer to use. And then here's the high-level API, which is much easier for a programmer to understand or someone working at the TensorFlow level. And we actually think that this can be automatically done by the compiler, but we haven't looked too far into that yet. Okay, so we implemented this in two different cases. So one was cached arrays, which are used for dense tensors. So this is, again, looking at training CNNs. And then the other one was cached embeddings for embedding tables for things like DLRM. So just like the talk that we just heard, we're also trying to optimize this in these kinds of systems. So we annotated these two workloads with our high-level data management interface and then implemented different policies. Excuse me. So here's our results for DNNs. So on the left is the cache, 2LM, which is just using the hardware managed cache. And on the right is the cached arrays with all of our different optimizations applied. So we were able to apply different kinds of optimizations, and we get significant performance improvements. Even for, in this case, we're looking at the workload is not, we're not doing this statically ahead of time. We're doing it dynamically as the workload is running. A couple of takeaways here. One is prefetching doesn't always help. In fact, prefetching into fast memory can hurt, which is what we're seeing here. And so this is an argument for why we need a dynamic policy for this. And the other one is some of our optimizations that we're applying. So by applying some of these semantic knowledge from the application down to the data management layer, we're actually able to get better performance in the caching mode as well. And then this works not just for dense systems, but this also works for sparse accesses. So again, thank you so much for giving an overview of DLRM and embedding tables, so I didn't have to. As we saw last time, these accesses to the embedding tables are pretty sparse. And so this is two different embedding table lookups. The left is very sparse accesses, so no locality, completely random accesses to it. And on the right, we're using a ZipF distribution, so there's some locality and some reuse in the embedding tables. And what you can see is, again, on the left is using a cache, on the right is our software managed data movement. We're getting significant performance improvement in training these systems if we use software managed data movement instead of the automatic hardware managed data movement. Okay, so to kind of quickly summarize this, things like AutoTM are really great, but AutoTM was bespoke. It really only worked in a small set of workloads, just CNNs, just static compute graphs. And if we went down that direction, every kind of workload is going to need a new management layer. Programmers are going to have to come in and figure out how to move data again and again for every workload. So what I want to argue for is something more like this data management API, where we can separate out the low-level details of how we're moving data around from the high-level use of the data at the software level. And I think that there's a path towards hardware acceleration when we use these kinds of APIs. Okay, so to conclude, memory systems are becoming increasingly heterogeneous. That's why we're here. And if we naively apply yesterday's solutions to moving data around, it's just not going to work. This doesn't work in these heterogeneous systems. And I really think that hardware-software co-design is the future. And specifically, I think we need to involve the program, not the programmer. So all these things that we were doing still keep the transparency that hardware caches have to the application programmer. It's just the middleware programmer that now has to understand these kinds of data movement things. And we really need to co-design both the data movement and the data placement. And then the one bullet point that I don't have here, which is also very important in our group has been working on, is we need to be thinking about security in these systems as well. I'll just say that. Okay, so thank you very much. Couldn't do this work without all of the great students and collaborators that we've had. And I think I might have time for like one question.
Hi, great presentation.
There's a switch on it somewhere at the bottom.
Hi.
I think it's on now.
Okay, I'll just say.
There you go. No. Oh, okay.
Okay, great presentation. But so one thing is that you are making the case for having a data mode API for, let's say, more diverse set of applications. But does this mean we are giving up on abstractions like virtual memory, where the application did not see what's happening, which physical resources does the data actually lie in, and the operating system does it for you?
That's a really, really good question. So are we giving up on virtual memory? So no, we're not giving up on virtual memory, but I would argue that virtual memory is not the right semantic or not the right interface for doing data movement. Virtual memory is great for managing the this resource of memory. Virtualizing it makes a lot of sense to manage multiple processes accessing this memory or sharing the memory at the same time. But I don't think virtual memory is good for protection of that memory, for security. It's not the right mechanism for that. And it's not the right mechanism for moving data around from one thing to another. You lose the information about the object. You lose the information about what the usage of that object is going to be when you use virtual memory, just like you do in hardware managed caches. It's a really good question though, how to, and that's the research we're doing now. How do you marry these things together?
And one more question about the hardware DRAM caches. Is it possible to, let's say, separate out your data accesses or data access patterns from your application into two parts? One that is good for hardware-based DRAM caches, and the one that you want to, let's say, manage with these data management APIs.
Wonderful idea. Yes. Okay, great. Thank you so much, everybody.
Oh, thank you so much. Because of the time, we were going to the next.